Welcome to Hot Chips 28. Session 3, Energy Efficient Computing, Low Power SoCs.
Good afternoon. Our next speaker is Peter Barry from Intel. Peter is a principal engineer in the Intel's IoTG group, Internet of Things group. And he has over 25 years of experience in embedded systems. He has worked from all the way from Z80, 68K, PowerPC, ARM, and now Intel processors in this space. And he has also, his other interest is mountain bikes. So let's welcome Peter for his talk on design and development of an ultra-low power Intel architecture for SoCs. Peter.
Thanks very much, guys. I think I definitely drew the short straw being up after that presentation. I've got no nice videos, no lenses, nothing fancy at all. So I'm going to just talk about Intel's experience in developing a microcontroller. I guess we're known for high-end CPUs, but we're flexing in every dimension in terms of compute, and we've developed a very low-power microcontroller for the embedded IoT market. Just going to touch on some of the the legacy aspects of some of the choices we've made, going to some characteristics of MCUs, because maybe part of the audience isn't that familiar. Just briefly talk about the D2000, the actual device itself, and then some of the actual trade-offs we had to do day to day in terms of developing the microcontroller. So this is the year I graduated, 91. This is what a computer for $7,500. I never actually got to use one this expensive. My boss did. I got the 286 hand-me-down. This was a very capable machine back then, and when you look at the compute performance that we have instantiated in the microcontrollers today, effectively the lowest end are at par with the CPU performance of those kind of devices back then. So the device we created was a 33 megahertz Pentium instruction set, and again comparable to the compute performance way back in 1991. So microcontrollers, they're primarily designed for battery operation and running for a very, very long time. They typically have integrated flash and SRAM, so that generally drives the process technology that they run on. So not all process technologies have flash. They're typically very much a mixed signal device with DACs, ADCs, comparators, and in the context of IoT, they generally have radios. The device we created initially does not have radios, but our subsequent devices all have integrated radios. Typically, the radios are the appropriate radios for IoT devices, which are nominally Bluetooth, BLE, 802.15.4, and low-power Wi-Fi. The duty cycle, or the use cases themselves, are dominated by duty cycle. Now, all kind of compute platforms have a duty cycle aspect. But when you take it to MCUs, effectively, you're talking about predominantly being idle and then having very small bursts of active states. The duty cycles for a normal use case, maybe a temperature sensor in a room, might be every 15 minutes. So it's largely idle and then just executing for a very small time, we'll say getting a sample from an ADC and then sending a packet out on the radio. When you're doing the design, effectively, optimizing for idle power becomes a very significant aspect of what we do. Because the applications are so varied, generally speaking, the power state management is all done in software. So it's not taken care of by an operating system. Your application itself is tightly coupled into managing the actual power states of the SoC itself. What we're optimizing for effectively is long-term battery life. So modern MCUs or microcontrollers typically go now up to 10 years off of a coin cell. And a coin cell battery is about 200 milliamp hours. So it's got a very, very small amount of power density. And when you, as I said before, when you're touching on the application itself, you're trying to optimize for very little activity and sleeping the device as much as possible. I'm going to drill a bit deeper into these kind of duty cycles to show where the power goes in the SoC itself. Hopefully you can see that. So on the bottom end, effectively, you've got all of the power that contributes to the idle state itself. So you've got some sort of wake logic. Even though you're idle, you're going to have to wake up from some source. That source could be a real-time clock or an input, a digital input or a comparator input. Typically, you don't want to boot the SoC every time you wake up, so you're going to have some sort of SRAM retention logic. So you're going to have some state information held for the CPU to start executing when you wake up. Your real-time clock and your oscillators often dominate the power consumption in this phase, in this state. And then you've just got leakage itself. Now, the first part we created in 180 nanometer TSMC. Newer designs are on 55 nanometer. So we didn't have an awful lot of things to worry about in context of leakage because it was such an old process. And then when you're optimizing for the active state, you have to minimize the time spent in your active state. That active time consists of your oscillator ramp up. So in your idle state, you're not going to have any oscillators except a slow frequency clock running. If you want to run the CPU at, let's say, 30 megahertz, you have to bring up the oscillator. You're going to have things like interrupt wake-up times. Then you actually do your workload, so you've got some time spent on the processing loop. And then you start optimizing that time by having very efficient core mark implementations. And then you go back into low power state. So when you look at the overall duty cycle of the application and the battery life, you're optimizing across all of these different vectors to make sure that you extend your actual battery life. And being cognizant of the application that you run is really critical because the software has to be tuned and optimized to make sure you get this extended battery life. The product architecture itself is very much driven by the process selection. Because I said we implemented on TSMC 180, we didn't have to do an awful lot of power idling on this device. As you get into the lower geometry nodes, the leakage of that node goes up, and typically you have to partition the design much more significantly to do active power management and state retention at a much more fine-grained level. The SoC that we designed initially, again, this was just our kind of first entry into the market. This SoC didn't have to do an awful lot of power management in terms of power idlings because of the process node we selected. I'm just going to go briefly over the actual device itself. So one kind of marketing glitzy slide. So we have the IA processor, again, running at 32 megahertz. We have 8K of SRAM on this device, and 8K of one-time programmable flash, and 32K of integrated flash. Some DMA controllers, and then usually a bunch of low-speed analog interfaces. So we've got a DAC, multi-channel DAC, multi-channel ADC, comparator inputs, and then we've also got the slow-speed digital I/O, which is typically I2C SPI for additional interfaces. And then we have just some power distribution, like voltage regulators on die, and we have typical JTAG and debug support. And then from a software point of view, we have just a standard ID to debug and program the software into the device itself. So let me just touch on power to kind of set the scale here. Again, with duty cycle and long battery life, this device is a 35 milliwatt active part and less than 10 microwatts in its idle state. Most of the power is in the actual SoC framework itself. Very little power is consumed by the actual core itself. I'm just going to go into some of the trade-offs, I guess, in terms of bringing an x86 down into this down into this footprint. One of the key things we had to optimize for was the actual die area. So in order to reduce the die area of a normal x86 core, we had to look at the instruction set available to us. And we iterated back and forth, like, should we reduce the instruction set? Should we take a thumb kind of model out of the ARM book and reduce the actual IC itself? We looked at whether or not we needed SSE, what kind of floating point to implement. At the end of the day, for the microcontrollers, we just needed a very simple instruction set. So we went back as far as the Pentium instruction set, which was the last well-supported instruction set baseline from an x86 point of view, and supported by the compilers. We also looked at system-level trade-offs, and I'll touch on some of the aspects here. And again, most of the optimization was associated with performance, area, and power. So we didn't need to get to extremely low gate count because the SoC itself is largely dominated by all of the other devices on the SoC. Our target was 100K gates for the CPU, and we achieved that. And then also the power targets were associated with reaching the 30 milliwatt active power state. Another aspect of the CPU design itself is we wanted to have a CPU that we could scale from an MCU right up just below the Atom performance line. This product, or this core itself, was used in a product called X1000, which is a full SoC which supported Linux. And we took the same core and we scaled it right down to support an MCU. So from an Intel's perspective, we didn't want to fragment and have loads of different CPU designs to cover this performance and power range. So we made this core itself configurable. It's an in-order 5-stage x86 Pentium ISA pipeline, or 5-stage pipeline with Pentium ISA, and lots of configurations in terms of the implementation options within the SoC itself, within the core itself, but also then the high-level actual features itself. The configuration that we picked for the MCU line, again, was Pentium ISA. We disabled things like PA, SMEP, which are security features. We brought the interrupt controller into the CPU, and I'll touch on that later. We didn't need a floating point unit for our particular design, so we turned off the x87 floating point. Because it was a very simple MCU, we pretty much had an AHB light fabric throughout the SoC, just a single fabric going out throughout the SoC. Again, max target of 32 megahertz. And then from a memory point of view, we wanted to have tightly coupled memories hanging off the device so we could have SRAM and flash more tightly coupled to the memory. We had TLB entries and we turned off the cache. And then we have single engine port memories throughout the device. Okay, as you can imagine, instruction set architecture in a company like Intel is a long conversation in terms of what flexibility and differentiation we can introduce into the instruction set. In some cases, it's quite rigid. In other cases, we had a lot of flexibility. In this particular product, as I touched on, we just went back to the Pentium baseline. The compiler support was there, the debuggers are already there, so we didn't have to do any changes to the software ecosystem in order to support this device. And as I touched on, we drove the implementation to meet the area, power, and performance targets. In terms of binary compatibility, in terms of the x86 kind of world, binary compatibility is usually a tremendous value, along with operating system support like the traditional shrink wrap Windows and Linux. In the context of MCUs, binary compatibility is generally less important. The MCUs themselves, the software for them is typically recompiled. They're typically running in RTOS, again, with source generally available for users to recompile. So binary compatibility wasn't the primary objective, but being Intel, there wasn't really any good reason to deviate from that ISA. We did look at optimizations about whether we could get a lower gate count, significant lower gate count, or a significant lower power by subsetting the ISA, but all of the analysis showed that there was no major significant gain to be achieved by reducing it in any significant way. At a system level, we had some similar choices to make in terms of what does the system present in terms of the standard architecture reference. We enumerate the features using CPID, so same as any of the x86 CPUs. But we made a choice to retain the paging and segmentation architectures within the device itself. Now, historically, those wouldn't make a lot of sense in the context of an MCU, but both paging and segmentation we can use very effectively to provide memory protection. So instead of having a memory protection unit, which would be the normal design in an MCU, we brought that protection into the core. And that allows us to have more fine-grained control and protection within the applications themselves. So we get more robustness in terms of developing the MCU applications. Now, obviously, you're not going to have paging running on a CPU of this size. So we retain the paging, but we set the TLBs down to just 2 instruction TLBs and 2 data TLBs. And we effectively preload them to give us our protection. So we don't actually do a page walk. We don't have page tables, but we can preload the TLBs to give us the effect of having done a page walk and give us that level of protection. And that avoided us having to do memory protection units in the fabric then. Another aspect that's very, very important for microcontrollers is the interrupt latency. I touched on it before in terms of the wake-up time. So the shorter that interrupt latency, the less time, less cycles you're wasting effectively in your active state. A traditional Intel CPU has a hierarchical interrupt mechanism with an I/O APIC, a local APIC, and a core, and the associated handshake mechanisms to establish what the interrupt source was. In the context of an MCU, we basically merged all of that function together and tightly integrated it into the core. We lost some of the flexibility that you have when you have a full I/O APIC and Intel APIC, local APIC in the device. But in the context of MCUs, you make effectively some design time decisions to choose the interrupt priorities up front, and then you can lock them into the design, which is what we did. We also did some interrupt descriptor table caching, so to reduce any kind of code fetching associated with the interrupt cycles. And we got our interrupt fetch time down to, let's say, 10 cycles overall from a wire being raised on the SoC to the first instruction being fetched in the core, which is significantly faster than any of the kind of standard Intel architecture devices with the hierarchical interrupt mechanism. We also had some trade-offs in terms of the flash integration. We had a very specific objective of having a very, very low-cost device. So just put it in context, the product itself cost between, the cost is about 50 cents and the ASP between $1 and $1.50. So a very, very low-cost device. When you're optimizing at that point, the actual flash becomes a significant portion of the cost. And the width of the buses associated with the flash cuts also becomes an aspect of trading off some of the costs. So in the development, we learned an awful lot about optimizing at a much more different scale than Intel's used to. So like we were optimizing sub-cent pricing on this device to meet our targets. So that actually, in fact impacted the width of the flash bus that we chose. When you're changing the bus width, that has an impact on performance. It has an impact on power states, whether the flash goes into its sleep states. So we effectively were optimizing across all of these vectors at the same time to meet the cost target, the performance target, and the power target all at the same time. Just to give a sense of some of the aspects that we looked at in terms of the cache infrastructure and its sensitivity to the performance of the device. So we were deciding whether or not to put a prefetcher into the instruction set pipeline. Initially, we didn't have one. And we were doing analysis to trade off whether or not it would be more power efficient to have a prefetcher in the SoC or not. At the end of the day, what we found is effectively it is still more efficient to have an aggressive prefetcher in front of the instruction set, or instruction pipeline, primarily because you did get the increased performance and it didn't increase the power as much. So if you look at the bottom with the prefetcher off, when the CPU is running at 32 megahertz, there was a drop in performance of 25% without a prefetcher, but the power reduction was only 11%. So we effectively, in most cases, or all cases, we recommend turning on a prefetcher. Another dynamic when you're looking at these kind of frequencies is that the weight states associated with the flash change depending on the frequency that you're running. So your core marking number, your performance actually depends on whether you're running your CPU at 32 megahertz versus 4 megahertz. Standard kind of benchmarking game is to quote core marks per megahertz and measure it at the lowest frequency because the weight states associated with memory are typically comparable to the CPU. Another trade-off we had to look at is to understand how best to fetch data from flash. As I say, we had a tightly coupled SRAM memory for the normal data references, but when you make a data reference from the flash device itself, we had to choose whether or not to redirect those data references out to the tightly coupled memory interface of the flash or let them go down through the memory fabric itself. In our case, we found there was no significant performance difference between just letting those data fetches go down through effectively the slower path through the HB fabric into the flash device. What we found is there wasn't much of a difference, especially in the benchmarks, because most of the data in the most of the literal data or immediate data was incorporated into the instruction set already as part of the x86 variable instructions. So we didn't have effectively literal pools that would have to be fetched using data fetches from the flash device. And also we found that in general, most applications, if there is a literal pool, you wouldn't leave them in flash, you'd move them up into the SRAM if you're concerned about performance. So we had a very simple implementation where data fetches to the flash effectively went through the normal memory interface. Then we had to look at the sleep states for the device. At the end of the day, because again we were on 180 nanometer, clock stopping was sufficient in this design. We didn't have to do any optimization for power state management of the core. Now that's something we have subsequently implemented in the core itself to have effectively what Intel calls a C6 state, where we can power off the core and save the architectural state in a small SRAM. That's more important when you get to process nodes like 55, where the leakage of the overall node is much higher and the core leakage will be much higher. I'll just touch on some of the SoC level trade-offs itself. Power delivery for an SoC that's running off a coin cell is very, very important. So understanding the loss in the voltage regulation is a significant portion of the overall loss in the design. So we used a regulator that had a few different modes. In its normal 1.8 volt rail mode, its switching regulator, there's a maximum current of 50 milliamps. It's 90% efficient when you're running at the high current of 50 milliamp. But it drops down to 70% efficient when you're only using 10 milliamps. Now, the SoC itself has a wide dynamic range in terms of the currents that it's using, depending on the application and what's active in the SoC. So we found it important to have a linear mode for the regulator as well, where when you're drawing much lower currents, the efficiency is far higher. And to put it in context, when you have the SoC that's largely dominated by its idle state versus its active state, switching the power delivery mechanisms into this very low mode as well in these active states is very, very important. Just in our case alone, we would get 30% battery life extension by switching into these lower retention modes and these different modes of operation of the regulation on die. As well as the actual getting the right regulators and the right modes, we did have to manage power delivery and power islanding just for the lowest power state itself. So while we didn't put the main SoC in any kind of significant power management modes, the always-on portion of the SoC had to be managed. And again, these are typical carefully managed kind of benchmark items in terms of how you wake up the SoC and what current it consumes when it's in its lowest power state. So generally speaking, the lowest power state that you can get any of these MCUs in is when they're in a very deep sleep with no real-time clock and they just have a digital wake-up signal. In our case, this is 1.3 microamps, right up to the case where you've basically got an alarm clock wake from your RTC, so you've got the RTC oscillator running. Everything else is pretty much turned off, but you've got a higher power of up to 3.4 microamps in our case. Another aspect of measurement another aspect of power management that becomes important with these kind of SoCs is because you're delivering all of your power from the battery into the SoC. The I/O rail itself is typically being supplied by the SoC as well. So you get a lot of cases where, depending on the actual I/O devices and their states, that can drive a lot of power in terms of your SoC as well. In terms of core clocking, it's just general. We can scale the core from 32 to 16, so just a very simple scaler. We did a lot of performance measurements again on this SoC to figure out whether or not, from a power efficiency point of view, you're better off running quickly or more slowly. The vast majority of cases, the standard race to halt is the best and most efficient way to do things. So you run as fast as you can and you go to sleep as quickly as you can. We did find in one case, though, for a very simple use case, running at 4 megahertz with, we'll say, I think it was an I2C controller active, the overall power was much lower. And that was because we were able to actually run the SoC regulators in this very, very low power mode and actually have some active use. So again, it was a trade-off of power islanding and leakage was the main aspects of choosing the frequencies. So in summary, It's our first iteration of an MCU, getting x86 into this kind of space. We are pretty proud of overall how we've achieved so far, but we're continuing to iterate on it. We've got microarchitecture enhancements, process-related microarchitecture enhancements, and then the analog I/O as well is the key aspect of evolution on the device. And that's it. Q&A.
We have time for questions.
Can't see it all.
Hi, this is Eric Xu from Google. I work in the consumer hardware group. This is definitely a low-power SoC. Just wondering if you have any thought on the security or authentication on the core flow, boot flow.
Say it again.
Consideration on the security and authentication of the core boot.
Oh, so the core, it boots from an OTP section of flash. So we have a one-time programmable area in the flash device itself, and that effectively is the start of any measurement that you might do. So we hard boot from that. We didn't put a ROM in there. We didn't have to with integrated flash.
And just to follow up, what kind of real-time operating system are you running?
What kind of RTOS? We're running Zephyr, which is an Intel or a Linux Foundation Intel-supported operating system.
Right. Thank you.
Shai Galan from Cavium. Wondering how you chose what benchmarks. How did you choose CoreMark to optimize for?
So benchmarks. So there's in terms of compute performance, it's CoreMark or DMIPS, right? DMIPS are largely not very reputable, I guess, at this point, right? The compilers are too good at optimizing for it. So the CoreMark is, in our industry, CoreMark for MCUs is pretty much the standard measurement of compute performance. There's another benchmark called ULP, which is ultra-low power benchmark, which is a duty cycling benchmark. We have the data for that, but it wasn't signed off to publish it. But because it's an MCU, ULP is very much a kind of standard benchmark for those use cases.
Thank you.
Any other questions? Okay, let's thank our speaker one more time. So our next speaker is Andi Skende from Nvidia. The next talk is on introducing Parker, Nvidia's Tegra next generation SoC. Andi is a distinguished engineer at Nvidia. He's a member of the Tegra team and Tegra lead architect. Prior to Nvidia, he comes from AMD. He was AMD fellow for 6 years. He was the AMD Fusion chief system architect. And he came to AMD from ATI, and prior to ATI, he was at Lockheed Martin. So let's welcome Andi.
Thank you. Hi. So today I'll be talking about the next generation Tegra SoC, codenamed Parker. And I'll be focusing primarily on some of the key features of the SoC. So when we set out to define the architecture for the Parker SoC, our primary objective was to build a high-performance processor targeting the premium automotive markets. We wanted to make Parker, first and foremost, a deep learning computing platform to enable the autonomous driving use cases. At the same time, our goal was to make it scalable such that it applied well to various use cases, to a wide range of use cases, from both performance and power viewpoint, starting with IVI, passive ADAS, all the way to autopilot and self-driving use cases. In the process, we also wanted to build a robust virtualization architecture. And the main goal here was to enable integration, to enable the tier ones and the car OEMs to be able to integrate into one single machine functions that typically currently are done across different SoCs or different ECUs. So virtualization, as you'll see later in the presentation, was one of the key focuses of this new Tegra architecture. So how does Parker fit into the overall NVIDIA Drive end-to-end deep learning ecosystem? On the left side, you have the training portion of a neural network accelerated by platforms such as DGX1. On the right-hand side, you have DrivePX, which combined with DriveWorks software stack enables compute vision and the inference portion of the deep learning. Parker, as you'll see later, is a critical component of the DrivePX platform, one of the critical building blocks of the DrivePX platform. So what is new in the Parker system on a chip? Two of the key improvements you'll see in the slides there. We first integrate a GPU core based on the most recent, latest, greatest Pascal graphics architecture. The CPU core is CPU complex. It's based on the second generation of 64-bit NVIDIA-specific implementation of the ARM ICE architecture. We'll have more information about this later. One of the primary focuses of the Parker SoC architecture was to enable functional safety to be able to support the automotive applications. And then, as I mentioned earlier, we tried to build an end-to-end hardware-enabled virtualization architecture that allowed good integration of functions into one single SoC. There were also a number of other improvements done that were more for internal benefit. Improvements to the SoC architecture to enable modularity and a more efficient design and verification flow on the ASIC side. And Parker Tegra was the first Tegra SoC in the 16 FinFET process by TSMC. Some more details in terms of what Parker brought in terms of features compared to the previous generation Tegra SoCs. So starting with the GPU, as I mentioned earlier, it's based on the Pascal architecture. It's really 256 CUDA cores that provide for roughly about 1.5 teraflops of FP16 compute horsepower. One of the main changes was in the CPU subsystem. In addition to the next generation Denver 2 CPU core, we created a CPU subsystem that was built out of two clusters, Denver plus A57, and together they're in the form of a coherent HMP architecture. And I'll speak to the goodness of that later in the slides. There were a number of improvements in the camera pipeline, starting with support for up to 12 cameras, but also improvements in the processing pipeline in terms of noise reduction and also supporting auto-grade HDR lenses. In order to support the very bandwidth-intensive use cases that we see in automotive space, compared to the previous generation SoCs, we went from 64-bit LPDDR4 to 128-bit LPDDR4 for a total roughly 50 gigabytes per second of bandwidth. In order to support the safety and resiliency, which is one of the key components for automotive applications, we built an ECC mechanism in and around the memory controller to enable ECC to and from the DRAM. The LPDDR4 RAMs do not come with embedded ECC by default, so we had to basically build an ECC in the memory controller and drive it from the SoC side. Another big improvement, in order to enable complex display configurations in the car cockpit, we went to three display pipelines, which are fully independent in terms of scalability, resolution, composition, overlays, and so on. They can support 4K displays up to 60 frames per second. Some improvements in the video encode and decode pipeline. We pushed the rate for both video encode and decode to 60 frames per second. Notable improvements in terms of the auto features. In order to enable a good integration of the Parker-based platforms into the car system, we brought two key interfaces controllers into the SoC. One is Ethernet AVB to enable streaming and audio and video streams from other ECUs through the Tegra SoC, but also to interact seamlessly with the rest of the car network. We have a dual CAN interface that can talk to the rest of the car network. As I mentioned earlier, since Parker is intended for automotive applications, resiliency and safety in the context of compliance with ISO 26262 was one of the key focuses of the architecture. So we made sure that the Parker becomes an automotive-rated SoC, first and foremost. We brought in a number of extensive set of resiliency features on die, the backbone of which is this safety manager engine, which I'll discuss briefly later. And as I mentioned earlier, we have an end-to-end hardware-assisted virtualization to enable integration into a single SoC of multiple car functions. And the last thing that I already talked about is TSMC's 16 FinFET process. So more on the Parker CPU complex. It is composed as a cluster, as two clusters, two Denver cores, Denver 2, Generation 2, plus 486 cores. Each cluster has its own L2 cache, 2 megabyte. The coherency within each cluster is handled through the L2. The coherency across clusters is handled through the coherency fabric, which is a homegrown, proprietary, NVIDIA-designed coherency fabric. Why 2 plus 4, and why 2 Denvers plus 487s? When we looked at the various use cases we cared about, we concluded that we needed a relatively high core count, therefore the number 6 that you see here. We also concluded that it was important to have a high single performance across all cores, single thread performance across all cores. Both A57 and Denver give a reasonable single thread performance. On the other hand, we wanted to not lose sight of perf per watt, especially for the low power use cases. So therefore, we included A57, which has a relatively good perf per watt profile in the lower side of the curve, especially for the sub-half watt range of the curve. At the same time, we wanted to have at least a few cores that have the highest single thread performance possible, and therefore the 2 Denver cores, which push the envelope on the single thread performance side of things. So that's why this 2 plus 4 configuration that we decided to deploy for Parker. In terms of the Denver CPU core, as I mentioned earlier, it brings a significant number of perf per watt improvements relative to Denver 1. It has roughly about 30% C-dyne reduction compared to Denver 1 for the same ISO process and ISO perf point. Similar to Denver 1, it is a dynamic optimization. In other words, it's based on optimized once, dynamic code microarchitecture, and used many times. It has some improvements relative to Denver 1 in the context of low power retention states, which I'll discuss briefly later. How does the Parker CPU complex in terms of raw performance, and we're using spec into 2K rate here, compared to the other competitive platforms. This benchmarking was done in a cold chamber, so from the thermal viewpoint, it's unconstrained. For full disclosure, there might be other throttling that happens in the competitive platforms due to EDP limitations of the package or the platform itself. But from a thermal viewpoint, this is unconstrained. So as you can see here, the total raw performance that the Parker CPU complex brings is roughly 50% to 100% better than competitive platforms, depending on which one you pick here in the graph. So, coherent heterogeneous multiprocessor, why that, right? As I mentioned earlier, having 2 microarchitectures that have their own special goodness from a power and performance viewpoint is something that we want to take advantage of, right? And that's why we put together a heterogeneous solution that allows us to basically schedule through a smart scheduler, schedule the right task on the right CPU core. And as the performance compute needs of the thread change over time, we can move the task from one core to the other to the appropriate core, thus maximizing both performance and responsiveness, but also on the other side of the spectrum, minimizing power. But in order to do this and not increase the overhead on the software by having software to deal with cache maintenance operation as the thread moves from one core to the other, we needed to build a coherent interconnect to allow, to make all this thread migration process transparent to software, right? And then we needed many cores for reasons I explained earlier, because most of the automotive use cases we looked at required relatively large core count, but also high raw performance, aggregate performance. So having what we call a big plus super similar to big plus little, right? As a reference to that, but big plus super. In other words, a big core and even a bigger core, A57 plus Denver. We get great single-thread performance. We have very good aggregate max performance, and we have sufficient thread count to support our most extensive, most complicated automotive use cases and gaming applications. So I wanted to highlight a few things here in terms of design challenges. Bringing two different microarchitectures into one single solution has its challenges, right? And the two key ones that I'm highlighting here are coherency and power management. The coherency protocol supported by Denver architecture is quite different than the one that we have in A57, which is an off-the-shelf ARM IP. And the differences are primarily a result of the dynamic coupled optimization that Denver has at the microarchitecture level. And that brings additional coherency state that has to be maintained and kept throughout the runtime. So natively, those two cores don't talk well to each other from the coherency viewpoint. So the coherency fabric that we had to build in-house, we couldn't use one off the shelf for reasons that I explained earlier, had to overcome those differences and bridge a gap between those two different coherency protocols. So it really represented a large design and verification effort. And a good time of the CPU design team was spent on design and verification of that coherency fabric. Power management is another place where there are substantial differences between an A57 and a Denver architecture. So we had to build a superset power state architecture and also a microarchitecture in terms of power management sequences that encapsulated both cores and obfuscated the differences in microarchitecture to the power management driver or kernel, such that it's not visible to that level. I mentioned, excuse me for a second. I mentioned virtualization as one of the big improvements in the Parker architecture. And as I said, it's an end-to-end hardware-enabled virtualization architecture. It supports up to 8 different virtual machines, guest OSs, but you can go beyond that. The moment you go beyond that, then you have to take basically a penalty through the hypervisor. So you have to go, for anything above 8, you have to go through a power virtualization type approach. As I said, the main goal of that was to enable integration of various car functions that until now have been done on separate ECUs or SoCs. For example, integrating IVI and instrument cluster in one ECU, it's one of the use cases we've seen talking to our automotive partners. It's one of the use cases that they definitely are going to deliver on. And each VM has the ability to control some of the key hardware resources directly, right? Display is one example. In order to basically maximize the efficiency of this architecture, it goes best with the Nvidia provided hypervisor, which is safety rated. That takes advantage, full advantage of our microarchitecture virtualization features. So some more details on what went into the virtualization architecture. And as I said earlier, it's kind of an end-to-end support. It starts on the ARM side, on the CPU side, with the virtualization extensions. And the main building block is the 2-stage translation MMU in the CPU core. That allows, from the point of view of the CPU, isolation across guest OSs in terms of accesses to memory as well as configuration space. The other side of the spectrum is the system MMU, which, similar to the CPU MMU, does the same by isolating the accelerators that are in the SoC, by isolating their accesses to the system memory. Also, on the GPU side, we made the GPU really fully virtualized from the point of view of how the VMs, the guest OSs, access the rendering channels. The GMMU provides for isolation of the various contexts from each other. And then to improve the real-time responsiveness of the automotive applications, we have improvements in both the preemption of both the graphics and CUDA compute workloads preemption to improve the responses in terms of real time. In addition, some of the other accelerators, such that the audio processing engine or the general purpose DMA, all their channels can be directly mapped to and accessed by a virtual machine. And all this is accomplished by starting, as I said earlier, with this CPUs and MMU, which gives you an isolation in terms of how the VMs access the configuration space of the various engines. The whole config space is 64 kibyte aligned, such that the stage 2 translation of the MMU can through the hypervisor, can isolate the access of the various VMs to the peripherals and the accelerators. Again, Parker is an automotive SoC. So what are some of the other key improvements made to make it an automotive SoC-friendly solution? On the I/O side, as I mentioned earlier, CAN and Ethernet EVB were two key additions to the I/O subsystem. We have a dual CAN interface. It is in the always-on domain, such that it can take wake-up calls from the car network and allow the wake-in sequence and booting sequence of the SoC that is in deep power state. It is a time-triggered interface between the two CAN controllers, and it conforms to ISO. On the Ethernet side, it's a gigabit Ethernet MAC controller through an RGMI interface that talks to an external fire switch, and the IP allows for real-time bandwidth reservations to improve QoS across multiple streams coming through that interface. The main purpose of this, obviously, is to stream audio and video streams from other ECUs from the rest of the car system into the Tegra SoC for additional processing. On the outer resiliency side of the features, Parker is designed as an ISO compliant, 26262 compliant SoC, and that really is comprised of two components, both on the systematic side in terms of design and verification processes end-to-end, as well as in terms of fit rate and hardware safety measures to improve resiliency and availability of the SoC. So we are ISO compliant. In order to enable all that, we have an extensive set of safety features, diagnostics features on the SoC in terms of error detection and correction. There is a real-time dual lockstep real-time processor that enables the error management and processing and reporting of that to the external system, but also allows us to run diagnostic libraries and recovery libraries to maximize resiliency and also maximize availability of the system. And the inline DRAM ECC is a key feature that builds an ECC solution, single bit correction, double bit detection around the LPDDR4 DRAM devices. And as I mentioned earlier, for some of the key on-die structures that have, by definition, high failure rates, we have ECC and parity for most of the memories on the CPU, GPU, and some of the memories, other memories in the SoC. Well, so as I mentioned in the second slide during the introduction, Parker is a key building block of the DrivePX2 platform, which is really a scalable platform that allows us to build flexible solutions that go up to 2 Parker chips combined or paired up with 2 discrete GPUs. And really, it allows the system integrator to, depending on its safety and performance goals for the platform, to build something that meets those, right? One example, if performance is the main concern, then you put two of these pairs of Parker and DGPUs together to maximize performance. If the safety goal or ASIL rating is the main concern and you want to achieve something very high, even ASIL D, then you use those 2 pairs to run redundantly and become a redundant copy of each other. So depending on the performance and safety goals that the system integrator has, then Parker, the DrivePX2 gives you that flexibility. It is developed as an safety element out of context. This is an ISO term. But the idea here is that when we set out to define the set of features that we wanted for both Parker and the DrivePX, we try to define a very comprehensive use case that gives us good coverage across the whole SoC as well as DrivePX platform in terms of safety features and resiliency features. But at the same time, we provide the system integrator and whoever is using the platform with our assumptions and our safety manual and safety supporting material in terms of FMEDA, FME, and so on. Currently, Drive PX2 is being sampled to multiple Tier 1 partners and customers. As guys probably have heard, Volvo is going to be using Drive PX2 into the next generation self-driving car. Yeah, I believe it's an SUV configuration. A bit more detail on the Drive PX platform. What I've shown here is the two Parkers talking to two GPUs up north at the top of the diagram. There is a PCIe switch in the middle that allows basically the cross-referencing of and cross-talk between Parkers and the GPUs. At the bottom, there is an ASIL-D microcontroller, which, depending on the configuration and the safety goal at the platform level, it can be used as, in the case of using those two Parkers redundantly to each other, it can be used as the decision maker and drive sort of a soft lockstep between the two. But also, it is the place where, if there are failures, faults in the SoC due to an ECC double bit error, for example, I wasn't corrected, those errors get reported from the Parker SoC to the MCU, and the MCU then is responsible of bringing the system to a safe state, and therefore taking over the functionality of the platform. So depending on the safety goal and the safety use case, it's a relatively flexible way of giving you the right configuration for your specific use case. So in summary, what is Tegra Parker? It brings in the next generation CPU core, which has an improved perf per watt and higher single thread performance relative to the previous one. It's got an exceptional aggregate CPU performance across all 6 cores. It is a flexible programming model through the HMP architecture in the CPU complex. It integrates the latest best-in-class GPU core based on the Pascal architecture. It does represent a flexible automotive SoC that can be applied to a wide range of use cases. And as I mentioned in the last slide, it is the main building block for the Drive PX2 platform that Nvidia has put together. So that's it on Tegra Parker SoC.
Thank you, Andy. We have time for a few questions.
Yes, Nathan Brookwood of Insight 64. There have been a number of reasonably scary stories over the last year about hackers taking over cars, either with some autonomous features, sometimes no autonomous features, and basically seizing the control function, causing it to steer or turn the engine off and so forth. Is there anything you've put into Parker in order to harden it with regard to its hackability?
Well, so on that front, the virtualization architecture certainly helps, right? Especially if you're running untrusted context and trusted context. So I'm taking an extreme case, right? You have IVI and potentially self-driving car type use cases, context is running at the same time on the SoC. Having a robust virtualization architecture, which Parker does, prevents you from having that Android side or untrusted context side taking over the driving functions that are running on the SoC. That's one. Secondly, there are a number of improvements made to the security architecture, which I haven't covered in the slide deck, which go hand in hand with safety improvements that certainly maximize protection in that context with regards to hackers taking over the system. Starting with a trusted boot, we have a very robust trusted boot sequence that establishes a root of trust across the entire SoC. In addition, trust zone is a big component that we are deploying across all the IPs in the SoC. So it's a combination of measures. It's not just one thing.
Have you hired any hackers to try and
not that I know of.
Okay.
Okay, on that side.
Chris Rowan of Cadence. At the top of the presentation, you said that deep learning performance in automotive was a key goal. Can you quantify for us at all what's the impact of this relative to a predecessor like Tegra-X1 in terms of deep learning inference performance in absolute or relative terms, and what contributes to that, that improvement, if there is improvement? What directly in the GPU versus what in the overall infrastructure helps you on that dimension of key performance?
Well, so in terms of obviously GPU it's a major component of that inference part of deep learning, right, pipeline. In terms of the GPU performance, it's a big leap in terms of compute horsepower relative to Tegra X1. I mean, if you look at the overall graphics performance, it's up to 2x more. In terms of teraflops, as indicated earlier, we're talking about 1.5 teraflops, which it's at least 50% better than what TX1 had in FP16 type units. And certainly on the CPU side also, the large number of cores helps in that respect. So there's a number of things. As far as key benchmarks, I don't have anything on top of my head other than giving you some raw numbers.
Thank you.
Okay. This is Vidyasagar from Qualcomm. Can you please comment on the TDP of Tegra Parker when it's running at its max workload? I mean, what is the kind of trade-off that you had to make when you brought the desktop class GPU to the more like a handheld type of form factor? And the other question is about
which form factor? Sorry.
To an automotive form factor, or even I believe it's also intended for VR type of form factor as well, right? I mean,
yes,
one of the markets. So,
well, that's very, I mean, as you said, it's very much a function of the use case and the platform itself, right? The platform limitations. So we're optimized to run optimally at various points in the performance power curve, right? So we're optimized to run relatively heavy workloads on the IVI side, but also all the way to the other side of the spectrum on the battery-operated devices, right? So I'm not willing to or not ready to quote any power numbers here for you, other than say that we are trying to be efficient across a wide range of workloads and devices.
Okay.
Hi, this is David Lee from MediaTek. A quick question on the PX2 platform. When you have a two Parker cell checking, or when they are checking with each other, is it checked by the hardware automatically, or is it done by the software? And if it's how much is the check? You know, you compare every cycle by cycle, or you kind of have some aggregate?
No, it's not really a lockstep, right? A true lockstep, as you potentially find in like an R5 core, where you really have lockstep cycle by cycle. This is a loose lockstep. It's done by the software, which is a combination of software OS running on either of the nodes, but also software kernel running on the ASIL DMCU.
So the platform customer can decide.
That's right.
How
That's
they
right.
want it.
That's right. So it's really, that's why I use the term loose lockstep, because it's a software-driven lockstep.
Last question.
Yeah, non-Quark B semi. So I have a follow-up question to that gentleman earlier. So with the loose step dual redundancy, right? So what kind of compute power do you actually have? I think it's done through a combination of hardware and software. You just answered that. My question is, how much effective compute power do you have?
For the case of having redundancy?
Yes.
Redundancy? Well, so I had the number on the slides there that basically said across the two Tegra SoCs, we have roughly around 8 teraflops of processing power. So it's roughly 4 between the DGPU plus the iGPU and the CPU on the Tegra side.
Okay, thanks.
Okay.
Okay, let's thank the speaker again.
Thank you.